Okay, great. Thanks, Alan. Hi, everyone. My name is Dave. I'll be chairing this seminar as part of the ongoing IGS Global Seminar Series. This week, we're excited to have Harold Lovell from the University of Portsmouth in the UK, who will be presenting on surge glaciers. So, as per usual, we'll hold questions until the end when you can either use the raise hand function or drop them in the chat. But without further ado, I'll pass it over to Harold.
Thanks, Dave. Thanks to the IGS and the other organisers of the seminar series for the invite. Very pleased to be here. So yeah, I'm talking about glacier surges, and actually one of the main things you'll probably notice immediately is that I'm also sharing quite a lot of nice imagery of surges. So most of the images I'll be showing are of actively surging glaciers, and the credit for almost all of these goes to other people. So this nice example here, this is Sheila Brain in Svalbard. So what I try to do whenever I've got these nice big pictures, to tell you where the glacier is, what its name is, and obviously who's responsible for the imagery. So this is Sheila Brain in Svalbard, and Eric, one of the co-authors on this paper that I'm mostly going to be presenting today, took this great imagery. It would be remiss of me not to plug Eric's website, the Living Ice Project, and with others. He's got some really great resources on there for surges and other glaciological imagery. So yeah, do please take a look at that. I should say as well, what I'm trying to do in this talk is to make nice, easy links to anything I'm referencing. So I'm using quite a lot of QR codes. It may seem like death by QR code. Apologize in advance. Obviously, feel free to ignore a lot of them, but it might be something you want to come back to at a later stage and hopefully find the kind of the resource that I'm talking about. So as I mentioned, yes, we've had a paper out recently, which more or less I'm going to be talking about. So this is a bit of a shameless plug, but also hopefully a useful QR code, because this gives you an open access version, read version of the paper. So please do get yourself a copy of that. But obviously, if any issues, just send me an email as well, and I can send a copy over. And yeah, again, you can come back to this one later. And the co-author team for this is fairly extensive. So obviously, I want to thank everyone who's been involved in that. Yeah, it was a really interesting project. 18 months or so putting together the piece of work that I'll be talking about today, and is in that paper. So yeah, thanks again to everyone who shared their knowledge from all the different kind of geographical locations where we find surge-type glaciers. So the talk is more or less going to kind of work through the structure of the paper through the key sections, but I'm going to start by explaining what we mean by glacier surges, or what we understand by glacier surges. What are they? What do they look like? What do they do? And then move through to some of the more interesting things we can look at in terms of surge behavior, the reasons glaciers surge, and the impacts that surges can have in terms of glacier hazards, and then finally thinking about climate change and the impact that climate change is having on surges. So the fundamental question, what we're talking about with glacier surges, well, these are ice flow instabilities, and they involve large increases in ice flow, acceleration usually to several orders of magnitude faster than the glacier was flowing prior to the event. And during that, a large amount of ice mass is transferred from up glacier down to the terminus, and often that will trigger terminus advance. So this example you can see here, this is another of Eric's fantastic animations. This is Penkbrain in Svalbard, and we can see the ice accelerating and advancing down and advancing into the proglacial lake. And another really interesting thing about surges is they're often recurrent. So surges occur in the same glaciers repeatedly, usually over kind of multiple tens of years to potentially even longer. And the shorter period of activity where they speed up and often advance, that's what we call the surge phase or the active phase. And then the longer period of quiet flow or almost stagnant ice flow, often terminus retreat, that's what we might call the quiescent phase. Just to flip back one there. So just to kind of look at what a surge would look like through various different data sets. This is another of the surges in Svalbard. And again, on the right-hand side, we've got Eric's fantastic animation. This is Sheila Brain, the example I showed in the kind of title image. And you can see it accelerating and advancing and actually spreading out into the fjord. This glacier was land terminating. It surged and advanced and became marine terminating. In the center, you can see this large transfer in ice mass with the DEM difference here. So we've got the red areas at the top of the glacier, almost splitting the glacier in two, in fact, where the glacier has lost elevation, and the blue area at the front where it's gained elevation. So it's really large-scale transfer of ice mass from the upper region of the glacier to the front. And then finally, on the left-hand side, we can see the velocity plot. So this is a massive step change in acceleration the ice is experiencing. So this is a plot from Gregoire Goulet's paper, where we see the kind of peak time of the surge in the center and then days either side of that from the peak. And as you can see, a really big step change in ice velocities for the surge itself, and then a kind of gradual decline over time. And we'll see some more velocity plots very shortly showing the variation in velocity profiles we see for a variety of surges. Another thing just to draw your attention to with Schielerbrain is that it actually formed a really beautiful version of a looped moraine. So looped moraines are always kind of used as classic examples of surge type behavior, where you see these sorts of teardropped, elongate moraine loops on a glacier surface. That usually tells us that a glacier has surged in the past. And if you look at the time step 1 satellite image, you can see the medial moraine between the tributary and the main trunk of Schielerbrain, slight deformation there. And then basically as Schielerbrain has advanced and surged, it's taken that medial moraine and extended it a long way down glacier and created this really distinct feature. So we see that quite a lot in this as kind of a smoking gun for surge behavior where we see that. Staying in the same fjord, in fact, but slightly further to the south, this is the Skøbrain-Paulabrain system, and this surged in around 2003, 2005. And I'm just going to point out some of the main components of a glacier that are involved in the surge. So we've got the satellite image here on the left-hand side, and then we've got the kind of reverse image looking up the glacier. And we have kind of two main sections with a surge-type glacier. We have something called the reservoir zone, where it will build up mass. So this is usually in the accumulation zone, but not always. But mostly we would talk about this as being in the upper reaches of the glacier. And then we have something called the receiving zone, which is pretty much always in the ablation area of the glacier. And during the surge, we'll see this transfer of mass, this rapid transfer of mass from these upper elevations down towards the glacier front. And this is very clearly seen here. We've got Skøbrain, the tributary, this glacier here up in the higher part. And then we can see the extension of the glacier and the crevassing at the front, telling us that this is pretty messed up extensional flow as the glacier is accelerating. If we actually look right up into the reservoir zone, into the accumulation zone, if you like, of Skøbrain, after the surge has occurred, you can see that there's this really big drop in height. So the pre-surge glacier height is shown by this line, and then following the surge and this transfer of the ice mass to the glacier front, you see a really big dip, tens of meters of reduction in the elevation of the glacier, and all that mass being transferred down to the front. As that mass is transferred, so this is the same system, Paulabrain, Skøbrain, we often see that as a kind of big topographic feature on the glacier surface. So this is a really big, what we might call surge bulge, surge front, extending from up glacier to down glacier. And this travels like a wave, effectively, of ice as that ice is transferred from kind of higher to lower elevations. Another nice animation here. This is in the same fjord again, slightly further north. This is Velekrobrain. And as we can see, when we get to the kind of surging ice reaching the front, the image here shows that actually features as a really clear topographic step. It's almost like the glacier is extending and advancing over another glacier. There's in fact the same glacier, and it's this kind of wave, the topographic waves traveling down glacier. The same glacier viewed from the front now, and a year later, and you can see this topographic step within the glacier itself, very clear. And if I just zoom in on that, you can see it's not a minimal feature. It's a pretty substantial ice cliff, effectively, in the center of the glacier. This wave of enhanced mass traveling down glacier. Again, 10 meters tall. And obviously, when the surging ice, the transfer of that ice reaches the front, we very typically get an advance, not always, but often. And this is back to Scobrain Paolobrain. This is one of probably only a handful of great examples of time-lapse imagery of an advancing surging front. And you can see that these are kind of almost images, daily images, depending on weather and various other factors, showing how the glacier is advancing out into the frozen fjord initially. Just draw your attention to quite a mess being made of the moraine area, the foreland. I'm not going to dwell too much on surge geomorphology, but it does create some really weird and wacky things that we can use to decipher past surging from the landscape. So what I've kind of talked through there, we can kind of schematically look at in stages according to the different parts of the surge. So we've got an increase in ice mass at the top in the reservoir zone during what we might call late quiescence, so immediately before the surge, and the front is receding. Then we've got this transfer of the ice from kind of higher elevations to lower elevations, an increase in ice velocities, and we see this topographic step. Eventually, the whole glacier is extending and advancing as that ice mass reaches the front, the highest velocities of the surge, typically at this sort of point. And then eventually the surge will terminate, and things will start to calm down again. The ice velocities will drop, and we'll see the terminus retreating. So this is a kind of a classic, not saying it is an example of every single surge, but it's only a classic kind of land terminating, down glacier propagating surge. We also see glaciers which start to surge at the front, and that propagates up glacier, and this usually is for marine terminating glaciers. So we can see another example from Svalbard, from some of Heidi's work, where the crevassing during the early part of the surge actually starts to extend up glacier. And we can see that kind of begins at the front as an instability, and then extends up glacier and increasingly including more and more of the glacier area into the surge. The velocity profile is showing us the same thing. So we're kind of going forwards in time from bottom to top, and the kind of brighter yellows and reds is the faster velocities. You can see as the surge progresses, the velocities are extending further and further up glacier. So this is the surge triggering at the front and propagating up glacier. We also see this from some of Eric Schiet-Maderfeldt's work looking at low coherence from radar imagery. So this is basically evidence of disturbed flow, which is telling us that a glacier is surging. And again, you can see Stonebrain and Svalbard triggered at the front, and this instability extended up glacier. The neighboring glacier, Deltabrain, actually contiguous with Stonebrain, you can see that the instability, the kind of disturbed surface flow, initially starts in the middle and then triggers both up and down glaciers. So we have very interesting patterns of kind of surge propagation that we see from lots of different examples. And then this second diagram just kind of schematically explains the up glacier propagating surge, triggering at the front, drawing down ice, and again extending, and then eventually shutting down and carving back. One of the really interesting things about surges is that we see them occurring in all sizes and scales of glaciers. So all the way from kind of small cirque glaciers like this one in Iceland, Burfellsjökull, all the way to the Vavilov ice cap in the Russian Arctic on Seven Eyes Emler, which has been, I believe, still going, but certainly been surging for a long period of time. You can see how it's really drawing down a huge amount of ice from this ice cap and extending out into the ocean. So that was a bit of a whistle-stop tour through what we mean by surges. Now I'm going to say a little bit more about the kind of diversity in surge behavior we have, and particularly the fact that there is no one size that fits all when it comes to surges. So the key thing to say is it's very hard to define what you might call a typical surge, even though I've given it a go, and I'm going to give it another go here. So a lot of the surge durations tend to be about 1 to 2 years to around 10 years, depending on the glacier and the regional location. We usually see increases in velocities during that surge active phase of kind of 2 to 3 orders of magnitude greater than during the extended quiet period or the extended quiescence. And then usually those peak velocities are around about 5 meters a day or higher, can be much higher, can be 20 meters per day, and as you see in some examples, even higher again. And where we do get surges occurring again and again in the same glaciers, that recurrence interval can be anywhere from 5 years to well over 100 years. So quite a lot of diversity within those examples there, but we see a huge amount of diversity globally and even regionally. So this plot here from Svalbard shows us 5 different glaciers that were all surging at around about the same time in 2016 to 2022 in this kind of 6-year period. And you can see the velocity profiles for those glaciers are all quite different. None of them, there's no 2 surges that occurred in that period that were the same in terms of how fast the surge started, the peak velocities, and the kind of nature and behavior of the slowdown of that surge afterwards. So huge amount of variety even within somewhere like Svalbard. And if we go globally, this plot here just picked 6 glaciers, 2 from Alaska Yukon cluster at the top here, 2 from high mountain Asia in the middle, and 2 from Svalbard that we've just seen previously at the bottom. And again, not really much to be drawing your eye to apart from these plots here and showing again, these are all normalized, and you're seeing very different velocity profiles. Some surges start and end very abruptly, some have really big lead up times, and then have various pulses of kind of increased flow. Some like Negru Brain start relatively abruptly and then seem to take many years of generally step-like deceleration. So huge amount of variety we're seeing there. And this again from some of Greg's work, he looked at a variety of glaciers that were surging in these 3 main locations: Alaska Yukon, Svalbard, the Russian Arctic, and high mountain Asia, and then just kind of plotted their average kind of velocity profiles around the peak of the surge. And you can see that whilst there are some patterns that can be taken from this, we seem to see particularly relatively abrupt initiations of surges in Alaska Yukon and very abrupt terminations. Svalbard, we seem to see a much more gradual start and then a much more gradual finish, and over a generally a longer surge, total surge duration. High mountain Asia somewhere in the middle with relatively even spread of the kind of initiation and termination of the surge. But I guess the main thing to say is that there's quite a lot of variety we're looking at there. So we get very fast surges. So this is Iceland. This is, as far as I know, the kind of fastest surge that has been recorded. Now this is actually rate of terminus advance rather than measured velocities. But the surge itself, was looking at rates of advance of, over 100 meters per day at times during the 1963-1964 surge of Brúarjökull in Iceland. We get slow surges. This is the classic example of Trappridge Glacier in Alaska Yukon. We've got a series of images of the glacier. The one on the far left is pretty much immediately following a previous surge. And you can see how kind of broken up and crevassed the glacier is and fairly extended. And then we're seeing the kind of quiescent period. And then by the late 70s, a very clear development of this topographic surge bulge. The lower plot tracks the progression of that surge bulge over 20 odd years or so. And then here we've got the velocity profile. This is the more recent surge, and you can see that it started to increase ice velocities and then didn't really go anywhere. And it didn't, and for a long period of time, it was expected that the glacier would kind of see a much steeper rise in velocities, but it didn't actually do that, and it carried on, along a similar level before dropping away again. So this was seen to be both a slow and a fairly extended surge of Trappridge Glacier. If we go to the Canadian Arctic, we see surges that actually can last for multiple decades. So Iceberg Glacier on the left here, around 22 years at least of a kind of active surge phase where the increased acceleration and transfer of mass from upper to lower glacier. Similarly, on the right-hand side here, we've got enhanced velocities as part of an extended surge of Nitti Glacier, around about 15 years. The next slide, I'm sure you're hoping is going to be short surges, but unfortunately, I've gone for much snappier surge-like velocity evolution preceding glacier detachments. But effectively, these are kind of short surges, if you like. So we've probably seen examples of these glaciers which effectively are collapsing and producing these large avalanches. And what a lot of Andy Caird's work has shown is that preceding these detachments, we see surge-like velocity increases. including very rapid step changes up to the point of detachment. And so it seems that there's some kind of similar surge-like behavior that goes on within these very dynamic and abrupt detachment events. So again, lots of diversity in surge behavior, but generally, it's thought that there are unifying properties and mechanisms which hold this all together. And in fact, if you come to this talk to understand exactly why glaciers surge, then I'm going to disappoint you because this is probably the shortest section of the surge, of the talk. But I'm certainly going to outline some of the kind of main things we understand about surges, the commonalities that we think are occurring within most surges, and the kind of sorts of things that are maybe explaining why some glaciers surge and some glaciers don't. So we've got some kind of very idealistic kind of examples of what we might expect from various different characteristics and processes that are going on during the surge. So this is just a schematic. It's not meant to be directly representative. But we think we've got, increases in basal water pressure at the start of the surge before that ramps up very much in what we might call the fast surge phase, so the kind of period of highest acceleration, and then a rapid drop off during termination, particularly rapid in, say, like an Alaska Yukon type style surge, where we see the rapid decrease in velocities, but perhaps more tapered in some of these other examples where we see step change in glacier velocities. Alongside that, we see the kind of opposite mirror effect of basal friction, we can assume, where we're getting, steadily decreasing friction and then suddenly a big reduction in friction to allow the high ice velocities that we're seeing as kind of enhanced sliding kicks in. And again, you see similarly tailing off at the end, the increase in friction matching a rapid decrease in velocities, particularly in some of these surges where we see a really quick drop off. Whereas others, we're obviously seeing more of a gradual flow reduction. I should say as well, this line is not meant to represent surge velocity staying at a really high level throughout the surge. There's obviously huge variation, usually some kind of seasonal signatures in there as well. But it's just to kind of show us that during this surge phase, we do have this enhanced velocity period. And then finally, we've also got these mass changes that we know are going on. We've got kind of in the reservoir zone, higher in the glacier, we've got an increase during initiation, and that drops off as the mass is transferred down to the glacier front, and then obviously the flip of that for the receiving zone, as we're seeing the glacier losing mass at the front and then rapidly gaining it as the mass is transferred down the glacier. So our observations are showing that we've got a steepening glacier profile as the reservoir zone is gaining mass and the receiving zone is losing mass. We know that subglacial water pressures are increasing. We've got a reduction in basal friction. We've got high ice velocities as a result. And then we've also got this initial zone in most cases of surging, either propagating up glacier or propagating down glacier or propagating in both directions. So how to explain why these occur, why glaciers surge? Early surge theories focus very much on characteristics to do with the hydrology beneath the glacier. So the classic Kamatau model from variegated glacier, looking at temperate glaciers and changes in subglacial hydrology. The kind of other theory, if you like, and not to say that these are completely incompatible with each other, would be based on polythermal glaciers, so those in Svalbard or glaciers like Trapbridge Glacier, for example, where there's a kind of thermal control and perhaps a switch in the thermal properties within the glacier, which is helping to increase meltwater availability at the bed and then reduce friction and increase sliding. So those were the early theories. The unifying properties of most surges means that there's a drive towards thinking of a single theory which can help to explain surging, and that's taken two main approaches in terms of how people have done this. Process-based approaches includes the Ferguson et al. Studies, and that looks at how friction evolves at the glacier bed, particularly how that's driven by the buildup of mass, as we see in the reservoir zone, and then any feedback that you get between the subglacial hydrology and friction, and how that then allows kind of this instability to propagate in different directions across the glacier. There's also studies looking at the beds and how the underlying sediments and kind of weaknesses within those can help to potentially propagate instabilities. And then on the system-based approach, this is largely from work that Doug Benn has led, looking at how glaciers can be viewed as energy systems, and particularly interested in enthalpy, so the kind of thermal energy and meltwater that builds up and is dissipated within the glacier system. And Doug's kind of ideas there would see surges as being some kind of imbalance between the mass and enthalpy within a glacier, and the cycles of mass and enthalpy giving you these surge cycles rather than kind of steady state flow. So that's where we're at with kind of surge mechanisms, and lots of really good work out there, and plenty more to do, I'm sure. That brings me on to thinking about the kind of geographical distribution of surges. And this is, again, one of the really kind of interesting things about surge-type glaciers is we don't find them everywhere. We find them particularly in dense clusters in different parts of the globe. So in our study, we kind of did an analysis of where all the glaciers are that surge or have surged in the past, and we came up with a number of around 3,000 glaciers, around 1%, which is pretty much what you would have read in the literature for many years, to be honest. So 1% of all glaciers, but around about 16% at least of glacier area. So these are affecting a fairly large proportion of glacier area globally. Our main two kind of sub-regions, if you like, are what we might call the Arctic and subarctic cluster. We've got Alaska, Yukon, Canadian Arctic, Greenland, Iceland, Svalbard, and Russian Arctic. And then, of course, our high mountain Asia subcluster. And these two are kind of broadly split 50-50 in terms of where most of the surge-type glaciers are found. And in high mountain Asia, all the way from Tian Shan in the north, the Pamirs, Karakoram, Himalayas, Tibetan Plateau, and Western Kunlun Shan being our main kind of subclusters within high mountain Asia. And then we've got a few other kind of scattered other categories, you might call them. The largest of which is those in the Andes, and Daniel Falashi's been doing some great work on those surge-type glaciers in the Andes. I'm not going to go through every single cluster because that would probably be the rest of this talk, but I did want to mostly show this wonderful graphic from Adrian Luckman. So this is anywhere we're seeing rainbow colors effectively is a glacier that is surging in Svalbard, and this is between 2015 and 2021 effectively. So Svalbard is the densest grouping of surge-type glaciers globally, and surge-type glaciers account for about 80% of glacier area in Svalbard, and obviously they're very active. And you can see from this plot from Koch et al. As well that we've got at least 18 surges were occurring in the period covered by Adrian's graphic. So yeah, these are popping off all the time. Work I think came out this week by Strozzi et al. Actually extended this timeline of surging on Svalbard back to the early 90s, and they've found around at least 58 surge events during that time. The different colors here relate to surges starting in different eras, effectively 10-year periods. And so what you will notice as well is that this 2015 onwards period has actually seen a much larger number of surges than the periods before. So things aren't quietening down in Svalbard by any means. Seem to be increasing, if anything. And I just want to draw attention as well to another paper that came out this year, led by Will Harcourt, which is everything you ever want to know about Svalbard surges. So that's definitely worth a look as well. And then one more kind of really interesting hotspot for surging would be the Karakoram, high mountain Asia. Again, we're looking at about half of the glacier area in the Karakoram affected by surging. And this great graphic from Frank Paul on the right-hand side here. I use this phrase already, but you can really see how these glaciers are just kind of popping off almost pretty regularly. I mean, this is obviously a repeated GIF, but you can see all of these tributaries advancing out into the main trunks and causing all kinds of weird and wonderful flow patterns. So that's another really dense area of surging. In terms of the geographical distribution, we understand from kind of Heidi and Doug's work in 2015, Heidi Silvestre, that this is a climatic control. And these plots are kind of just an update on that work that was done before. So we're seeing surge-type glaciers in particular plotting in a different space compared to the population of non-surge-type glaciers. Kind of a Goldilocks effect. They don't like it too warm and wet. They like it too cold and dry, for example. But there is a sweet spot which controls where most surge-type glaciers are found. And then our two later plots kind of break that down. I should say we've got precipitation on the x-axis and median temperature, summer temperature on the y-axis. And our subsequent plots kind of break that down by these main clusters in the Arctic and subarctic and high mountain Asia. And you can see there's a kind of a separation out, from the colder and drier parts of the Canadian Arctic all the way through to the warmer and wetter parts of Alaska, Yukon. So climate has a big control on where glaciers are surging. And then there's other controls that we can look at as well, including glacier geometry. So perhaps unsurprisingly, glaciers that are larger and longer have also greater elevation range. These are all kind of connected, I guess, but they're more likely to surge than the population of non-surge type glaciers. And this is from all of the high mountain Asia surges from Greg's paper in 2022. And we also see that they tend to have lower slopes, but that's also probably related to these other dimensions. And then there are other things that potentially control surging, including underlying geology and so on. Okay, so I think I've probably got about 10 or 15 minutes left to kind of get to some of the perhaps slightly more interesting and novel parts of surging that we were trying to look at in this paper. And the first of those is kind of an appreciation of the dangers that surges actually can pose in certain locations. So this is Shispa Glacier in the Karakoram. This really angry looking black mass is the glacier which has been surging. We're going to talk about a lake just up here in a minute, and you're going to see some imagery from that. But I guess what's to point out here is that the glacier is advancing, and there's lots of infrastructure and things that the glacier can cause a problem too. I appreciate showing you a video with no sound is not the best thing, but this is one of my favorite videos of trying to say how glaciers can be hazards. So effectively, what he's saying is, if this glacier goes slower than 1 mile a year, we're all dead. And she goes, "Oh, get out of the way!" And he's not at all bothered. I think that perfectly encapsulates what most people might think of in terms of glacier hazards. That it's not really a great thing. This idea of glacier of doom. The ice is surely advancing so slowly that we're not so bothered. I guess what we found while we were looking into this is that actually they can cause hazards when they're advancing, and there's several of these that issues that can be caused, and I'm going to kind of talk through those. We've got glacier advance, ice dams, glacial lake outburst floods, outbursts of subglacial meltwater, glacier detachments, and then also things like increased crevassing on the glacier and enhanced calving. And this diagram is just kind of a schematic to illustrate some of those, but I'll kind of walk us through some of these main types of hazards now. Starting with glacier advance, and again, this is a really nice set of images from the Nachtferne in the European Alps, which is a history of surging in the kind of Middle Ages, to show, the kind of, I guess, the way that surges could be viewed as an advancing risk. And this is meant to be Finsterwalder, I believe, the famous glaciologist being swallowed up and spat out by the glacier. So in terms of some of the examples, so this is the Karjala Glacier in the Pamirs. And this is it advancing and surging, and it cascaded a bunch of boulders and ice down, which damaged some of these kind of animal shelters and also covered quite a lot of pasture land, so obviously presenting a disruption and risk to human activities. Moving over to the Andes, this is the Horcones Inferior Glacier, and particularly famous because this is Aconcagua, which is the highest mountain in the Americas, and this is one of the climbing approaches. So here is the approximate position of the lowest, I believe, base camp for climbing the mountain. The glacier surged, and as a result, they had to permanently move that base camp to a new location where the glacier could cause no more trouble. So these are examples of how glaciers surging and advancing have caused disruption and issues for human activity. Coming back to Shispa Glacier, we've already seen the angry front of this glacier. This is a nice example of how glaciers can advance and block off drainage in side valleys. So if you draw your attention to this part here, you can see a large lake forms really quite rapidly as the glacier is advancing. And then that water eventually will drain, and you can see it drain very rapidly. And it actually drains subglacially under the ice. And when it does so, it can cause glacial lake outburst floods, and in one case, destroying this kind of bridge over the Karakoram Highway. I should say this is not a repeated image. This is still going in time. So this lake actually formed a further 4 times and drained a further 4 times during this surge. So between 2018 and 2022, there was large lakes and gloughs occurring pretty much every year. So quite a large risk. And this is seen in other parts of the globe, particularly elsewhere in the Karakoram. I already mentioned glacier detachment, so I'm not going to dwell too much more on these. But again, this example from the Tibetan Plateau, side by side twin glaciers, which one after the other kind of demonstrated these surge-like instabilities, include the development of surge bulges in terms of the topography of the glacier, acceleration in the ice itself as well before collapsing. And sadly, this example, Aru 1, this one here, did cause some loss of life as well. When surges advance, they accelerate, and the acceleration stretches the ice, and that means we get really large crevassing. You've already seen from some of the imagery how crevassed these glaciers can get. And that can cause problems as well. So this map here is showing just some of the kind of main snowmobile routes around Longyearbyen in Svalbard. And then just behind that, I've got Adrian's surging map, if you like. And although these are not all the routes that people would take, but certainly for tourism activities and for getting over to Ny-Ålesund, for example, lots of these routes can be affected by surging at different times because the crevassing on the glaciers basically makes them impassable. And then bring it back to some mountaineering examples. So this is Denali, or I think it is something like Mount Trump these days, isn't it? And one of the climbing approaches to Denali is this glacier here, Hensil Nolu, or Mojo Glacier. And actually a previous surge, it surged relatively recently in the kind of 2019, I think, 2019, 2020. But the previous surge caused quite a lot of issues for the kind of standard climbing approaches, and they basically switched all the main climbing routes to the southern side of the glacier, of the mountain, because of the crevassing causing major issues. And then finally, in terms of hazards, we have enhanced calving. So when glaciers surge, quite often they will produce more icebergs during that period, and some of those can be quite large. Sometimes, in this example from Svalbard on the right, the glacier's surge will end, and then the kind of enhanced calving will occur. But either way, you're generating large volumes of icebergs, potentially in quite a short period of time. If we look at something like the potential shipping routes around the Arctic region, then we also highlight some of the main surge clusters in this area. You can see that there's potentials for kind of interactions between more shipping in these areas and larger volumes of icebergs. So something for consideration there as well. This bottom image is just the iceberg that supposedly sunk the Titanic, and I only put it up because my daughter's been studying the Titanic in school, and I said I'd put a picture of that iceberg in just for that. And then we looked at kind of a global analysis of where these different hazards are. So we identified at least 80 surge-type glaciers which have kind of caused disruption and hazards out and about there. And you can see that they're spread across most of the main clusters. The main type of issue we find is particularly ice-dammed glacial lake outburst floods, particularly in the Karakoram as a really high percentage. And obviously when you move up into the Arctic, it's more kind of potential enhanced calving affecting shipping and tourism and increased crevassing as well. Okay, so onto the home straight now. Just the final few slides thinking about how climate change is potentially affecting surging. So the kind of traditional view has always been that surges are kind of seen outside of the impacts of climate change. And often you see surges kind of discounted from studies of glacier change related to climate. But what we're increasingly seeing is that climate is affecting surges, not only where we find surge-like glaciers, but also their behavior. So we're seeing examples of surges becoming less extensive over time. So there's various glaciers here from across Alaska, Yukon, and Svalbard, where the surge is reaching a less extensive point for each subsequent surge. And obviously, there's a kind of a mass balance control. The glacier is building up less mass over the kind of each quiescent period and advancing less far. If we go back to the Trap Ridge Glacier example in Alaska, Yukon as well, potentially this is kind of a reducing surge magnitude, in that instead of entering into a classic surge peak, as you might expect from the previous surge that happened in Trap Ridge, it seems that the glacier was unable to kind of attain those higher acceleration velocities and kind of just faded away without really having the fastest surge. So potentially there's a climate control around that as well. We're seeing examples where glaciers effectively are surging and then are no longer able to surge again. And that's perhaps unsurprising, because a lot of these glaciers are expending a huge amount of their ice mass down to lower elevations. And obviously in a warming climate, that then makes them quite vulnerable. Usually it's the smaller glaciers which are suffering, but the example here on the right is Comfortless Brain, which is a fairly sizable glacier in Svalbard, surged around about 2008, 2009. And in the period since has really shown no signs of gaining mass in the reservoir zone to build up towards a subsequent surge. So it could be that some glaciers are actually kind of surging to death and are no longer able to surge again in the future under current climate conditions. We're also seeing extreme events like rainfall triggering surges. So this is Tuna Brain, another example from Svalbard, which had a fairly, you could almost say it was surging by clockwork, almost every 40 years. And then it kind of bucked that trend in 2016 by having a slightly earlier surge than might be expected. And that surge was actually preceded a very extreme rainfall event for Svalbard in October of that year. So it looks like potentially extreme weather could have helped to, channel waters to the bed and trigger the surge before it was really ready to go. We see that similar things in Alaska, Yukon, where there's been a kind of a correlation between the last three surges of Donjek Glacier, all of which happened in the wettest years, the wettest summers on record for that location. So potentially a link there between the rainfall and the surge. And then also it's been proposed in places like the Karakoram, kind of an increase in surging could well be related to some of these extreme melt events or higher snowfall. So there seems to be increasing evidence that climate change could be impacting surges, and in some cases even triggering them. And then kind of a final thought on climate change. So Eric produced this really nice plot. So the left-hand side, he plotted what we might call surge climate. So this is the climate that most of the surges are found in, and obviously that is showing areas which we know are proper surge hotspots in the darker blue, like Svalbard, Canadian Arctic, Alaska, Yukon, Greenland, Russian Arctic, and across high mountain Asia. And then in the right, he kind of projected that forwards under various scenarios to see what, where will these areas which are conducive to surging shift, and what would that mean for kind of the behavior of glaciers in those regions? Will we see some areas where glaciers will stop surging, some areas where they might start, for example? So one thing that you can draw your attention to is even in the kind of last period, and certainly into the future period, we don't seem to have the surge climate in Iceland. So is that telling us that we're not having any more surges there? And on the other side, in the Antarctic Peninsula, in both cases, we can see that the climate that surges like to occur in is already happening and will continue into the future potentially. So it raises these two questions, and we can kind of evaluate these very quickly. So, for example, Antarctic Peninsula surges, we actually potentially already see that happening. So this is from Stringer et al. From last year. James Ross Island and one glacier in particular, they showed that had this kind of classic multi-year increase in velocities, concurrent with some kind of elevation change and gain of mass at the front of the glacier. So for all intents and purposes, what looks like a classic surge, but this time on the Antarctic Peninsula. If we go back to Iceland, this idea of perhaps surging not happening any longer, This nice map here, you may not be able to read all the numbers, but effectively, most of these glaciers across Vatnajökull last surged in the 90s. And we had this kind of dead period where nothing was surging or seeming not very much was surging. So that seemed to feed into the idea that perhaps surging was ending. But of course, as soon as we raised those ideas, one of the glaciers has started to surge. So that's Dingjujukul up here in the north. And yeah, we can see the increase in velocities up to the same kind of speeds that we were seeing for the previous surge. So I think for now we can strike off this idea of no more surges in Iceland. And if you happen to read that in our paper, you can ignore it very quickly and move on with your day. Yeah, so just to kind of finish up with some perspectives on what perhaps would be useful moving forwards in terms of surging research, and obviously please do add to these. I think remote sensing data is great, and we see some really great advances in the technologies and the sorts of things we can produce, the sort of stuff that Eric and Andy Keb have been doing, for example. But we still need more, I think, and there's certain parts of the world which are data poor in this kind of direction. So that's always useful to think about. We also definitely need more observation from the beds of glaciers. That's something that is massively lacking and is very challenging to achieve, whether that's through instrumentation or other techniques to try to see what's happening within glaciers at the glacier beds throughout surge cycles. Ideally, we could extend these surge histories back in time as well. So looking at things like surface characteristics, which allow us to unpick flow histories, also looking at the geomorphological evidence that can tell us what glaciers have been doing in the past and how we can link that to kind of surge dynamics. Fundamentally, we still have lots of unknowns around processes that are controlling surges and how we can kind of develop better models to look at basal processes, and particularly these ideas of the switch between surging and non-surging, and why some glaciers are showing this behavior and not others. And then finally, we want to kind of build on what we were looking at in terms of how future climate change might affect both the distribution but also the behavior of glaciers, and potentially areas where surging might cease or start or happen more frequently or happen less frequently. All these sorts of questions that would be really interesting to answer. Final kind of plug, but also I'll dress this up as a final opportunity to get a read version of that paper if you haven't already, but please do email me otherwise. Once again, thank you to the author team that were involved in that work. It's been great fun to put together and hopefully of use. And yeah, I think that's all from me. So thanks very much for listening. This final QR code is just to my university webpage, nothing more than that. I apologize for all the QR codes, but hopefully they'll be useful to someone someday. And thanks again.
That was great, Harold. Thank you so much. I really, really enjoyed that. And you kept talking about the QR codes. I think it's great. Nicely cited presentation. That was excellent. I'll open it up for questions. Maybe I'll get us started with one. Kind of earlier in the talk, you showed three distributions of surges of different glaciers, and you had the distribution about the peak. I was wondering if you could hop back to that slide for a sec.
Yeah, no worries.
Sort of contrasting three different types of surges, or three different areas.
Yeah. Apologies. Fast forward. This is probably the quickest way to do it. There we go. Is that the one?
Yeah. Okay, so these are all centered, so days from peak, and so that's the normalized surface velocity. Okay, so Alaska, Yukon, you can see there's sort of this buildup of speed, same with Svalbard, but the high mountain area stood out as it's very like it happens very quickly.
Yeah. So I guess the first thing to say is there's quite a lot of variation even within these averages. And this is all Greg's work, I should say. But yeah, I think the idea here is that there is some differences in how these get started. and how they terminate. And particularly, as I think the most interesting thing is that in Alaska, it does seem that most glaciers, or this is a sample of 20 at least, is a kind of a more gradual step change in increase, but the drop off is really rapid.
Yeah.
Um, and they basically shut down very quickly. If we think of like the classic variegated glacier, which was this, well, still remains the gold standard of studies on surge type glaciers from the 1980s, with Barclay Cam and many others. They basically instrumented this glacier through surge cycle when they thought it was about to surge, and got some amazing data sets. And what that showed is that you basically get this very rapid dewatering of the glacier. So it kind of evacuate all of that, all the subglacial, higher subglacial water pressures, which are driving the surge, happens very rapidly in kind of a big outburst flood, effectively. And that just shuts down the enhanced sliding, increases friction, and slows the glacier very abruptly. Whereas clearly in places like Svalbard, that is happening as a much more gradual process overall, over several years sometimes, the deceleration.
Yeah.
Something like Negri Brain had a peak, and it's just been kind of gradually slowing back down to the pre-surge velocities, but still, for a long time, it's still flowing faster than kind of quiescence.
Interesting. I guess I had always thought of surges as sort of happening more on sort of like that week to month scale as opposed to years. And some of this shows that, like you're saying, it takes a long time to slow down. Interesting. Hester, I'll pass it over to you.
Hi, nice job, Harold. Actually, stay on this image because I just want to give a caveat. All these graphs are normalized, so you can't really compare kind of the slope of how quickly some things increase in velocity or decrease because the peak velocities are really hugely different between these regions. And just for visualization of the general pattern, we normalize them. So I had a question, Harold. You mentioned stepwise increases a couple of times, and here you showed for the Alaska Yukon kind of region that it's stepwise. But for some of the longitudinal profiles, you also like mentioned stepwise increases. Can you maybe explain what you exactly mean with that? Is that just a yearly kind of variation of every single year there's a stepwise increase, or is it really what we're seeing, or is it how we're plotting it?
Yeah, I mean, I guess I'm just using stepwise as a instead of like an abrupt acceleration to a peak, it's kind of a gradual increase, not necessarily as steps, but I'm just using it as a kind of over time increase. And sometimes you see jumps from year to year, which perhaps could So it's more of a term I'm using rather than anything. Yeah, I would literally
Right,
sound.
because we don't use the term in the paper. So yeah, it was a bit confusing. And for those who can't see the text, but the earliest time lapse that we know of or that's available is a variegated glacier 1982, 1983, and they actually put it on YouTube, so you can see the earliest time lapse of a surge, and it's quite impressive.
Great, thanks.
Interesting. Anyone else?
They're all too busy with the QR codes.
Yeah. Oh, someone unmuted. Who's there?
Sorry.
Yeah.
Hey, thanks, Harold. That's great.
Thanks, Bethany.
James Ross Island, like when I did some fieldwork on James Ross Island, we knew that it was in this kind of climatic envelope where we get a lot of surges. And one of the things that we were thinking about when we went there was, do we see much evidence of surging glaciers on James Ross Island or on the islands around there? And we didn't really see anything. And there's I think Chris Stringer's paper from last year, I think is maybe the first paper to identify a surge in glacier on the Antarctic, whereas they're not very common. And I was wondering why, although we have the right kind of climate, do you think we don't see lots of surge in activity on the Antarctic Peninsula?
Yeah, I mean, it's a good question. I think a lot. Though the climate is very similar to Svalbard, and this is what I read. I was reading some of those papers recently, actually. But I think the glaciers are quite different in terms of most of them are really large. Kind of. I mean, effectively, we've got an ice sheet there.
There's lots of little ones around the edge, though.
Yeah, yeah. So I'm not really sure. I'm not sure why we're not seeing more evidence, and perhaps it's because it's not been looked for. I think there's part of that. In terms of past evidence, I don't think necessarily some of these landscapes are going to preserve, the kind of classic surge geomorphology in the same way you would get in Svalbard or parts of Iceland necessarily. So yeah, I mean, and we've got a lot of presumably very cold glaciers. The thermal regime may have a part to play in that as well. But yeah, I think we should expect to see more, either by looking back with new eyes or particularly looking forwards.
Thanks.
Anyone else? We've got 3 minutes to the top of the hour, so we've got time for a last one if someone has something. And if not, oh, Bethan, there we go.
I'll ask one more question if nobody else wants to ask a question. I wondered what's next. What's the next big question for surging glaciers?
That's a good question. Mine or what should we say? I mean, in the paper we found
as a community.
Yeah, I mean, in the paper we make 5 or 6 kind of key recommendations. I guess we still don't have loads and loads of data, or very much at all, in fact, of what happens at the bed of the glacier during a surge cycle. And particularly, we don't have very much of that data from certain parts of the globe. So high mountain Asia, we have over half of the surge type glaciers, and yet very, very little in terms of knowledge of what goes on within those glacier systems. So we are data poor in some locations, and I think that would be a massive boost. Better measurements, better instrumentation in that part of the world. In general, we still only have a handful of examples where we have that sort of data from anywhere, and they're accessible glaciers, or we're still talking about the variegated glacier studies, which happened before I was born, which was obviously an amazing set of studies. But I think that there's room for plenty more of that sort of thing as well, and lots of different examples, particularly to try to get to the bottom of this diversity in surge behavior. I'm particularly interested in what's going to happen to surges as climate continues to warm, and are we going to see changes in behavior and distribution? We assume we will, but how's that going to look? Particularly if that means that there's implications in terms of the impacts on people, particularly in high mountain Asia, for example, if we're going to see more frequent surges or less frequent surges, or whichever way it might go. And then finally, I think, still kind of trying to refine these unifying surge theories and models of surging, to get to the bottom of, why is it that some glaciers show this what I think is really interesting behavior, and others are just, are not.
Thank you.
Great. There's a comment from Ivar there. Great. Well, thank you very much, Harold. That was a great overview of surge glaciers, and seems like a really nice paper that I hope people go check out. So thank you very much for taking the time, especially in the evening over in the UK. Thank you all for attending.